So when we have a graph, one of the fundamental things we can think about is ways to get from one vertex to another vertex by following edges. So informally we call this a path. So for example, if I start at B, I could get to H by following, so for example I could go from B to C to F to G to H. And so we call that a path in the graph from B to H. And so all of these vertices, there's different paths I can go between, to get between them. But there's no path, like if this is part of the graph too, there's no path from I to get to F, for example. Okay? And paths, pretty much anything that you can imagine modeling with a graph, the idea of paths is meaningful in that context. So, for example, suppose that the vertices here represent people, and the edges represent people that know each other, or maybe people that are friends on Facebook or whatever. And so in that case, a path would correspond to some chain of acquaintances that link you to someone else. And maybe you care about that because you want to try to find someone who can introduce you to someone and who can introduce you to someone else. Or suppose that the nodes represent locations in a city, and you want to get from location B to location H, and the edges represent roads or paths of some kind. And so a path in this graph is going to represent a route you could take to get from one place to another place. Or even more abstractly, maybe the nodes in the graph represent states of a certain puzzle, like a Rubik's Cube or some other kind of puzzle, and edges represent like a move you could do to move the puzzle from one state into another state. And finding a path from some point in the graph to like some solved state, for example, would represent a solution. So if you start in this maybe scrambled state, you do a bunch of moves corresponding to following a path of edges, and you can solve it. You could think of other examples. I mean, pretty much any example you can think of where we're modeling something with a graph, you can give some meaning to the idea of paths in the graph. So let's see a formal definition of what a path is. So let G be an undirected graph and by the way, I'll just mention that a lot of the stuff that I'm going to be talking about has to do with undirected graphs. When we talked about vertex degrees, we talked about undirected graphs. Almost everything that we're talking about, there is a nice generalization of it to talk about directed graphs. So for example, with paths, we can talk about a directed path where you can only follow edges in the direction that they point. With degree, you have to talk about not just the degree, but you have to talk about the in degree and the in degree and the out degree. So the in degree is like the number of edges that are pointing into a vertex. Out degree is the number of edges that are pointing out. We're not going to talk a whole lot specifically about directed graphs, but you can keep that in mind, that almost everything that we talk about, you can think, a question you can ask is, what would be a natural generalization of this concept to directed graphs? Okay, so if we have an undirected graph, a path is an alternating sequence of vertices and edges so I'll just draw a picture of it. So we start with some vertex 0, and then we have an edge 1 and a vertex 1, and then edge 2 and vertex 2, dot dot dot. Finally, we'll have like vertex n minus 1, edge n, vertex n. So maybe we'll say, such that successive vertices and edges are incident. Right, but this is just formalizing the obvious idea that we start at a vertex, we have to go across an edge that's connected to that vertex, that's incident to that vertex, and go to another vertex and keep following edges like that. We can't like skip, from some vertex to something else that's not connected to it. Okay, and we'll say such a path has length So for example, in this graph, I've got like, if I go from B to H along that path we were talking about before, we go to C to F to G to H. That's a path of length 4. So it's important to keep in mind that the number of vertices actually is going to be one more than the length. For the length, we're actually counting the number of edges. So it's like how many steps do you have to take? So 1, 2, 3, 4. There's also some other paths of other lengths. So for example, we could go 1, 2, 3, 4, 5, 6. I think 4 is the shortest we can do though, right? Okay. And then another thing we can say is that a cycle is a path where v0 is equal to vn. So in other words, we end up in the same place where we started. All right, so this graph has some cycles. For example, if we go C, D, F, E, and back to C, that's a cycle of length 4. I think there's some other cycles of other lengths, so you might want to try to find, see if you can find any cycles of other lengths in here. Yep. So, a couple other definitions. So, we talked before about how like we could get from B to H, but we couldn't get from I to F, for example. So, let's make that formal. Two vertices are connected if there is a path let's say a path which has them as its endpoints. Okay, so we would say B and H are connected in this example, but F and I are not connected. B and C are also connected because there's just a path of length 1. But B and H are not adjacent. They don't actually have an edge directly between them, but they are connected. So there's a series of edges we can follow. And then the other thing we could say is that a graph is connected if every pair of vertices in it is connected. Every pair of vertices okay, so this graph obviously is not connected because I've got, I and j are over here, and I can't get from I and j to anything else. If I didn't have I and j though, right, then what's left is connected. Because any two vertices I pick, I can find a path to get from one to the other. Okay, and then write one more definition down here. A tree is a connected graph with no cycles. So this is definitely not a tree, right? Even if I get rid of these, it still has some cycles. So let's actually erase this. So let's draw a graph that is a tree. So it has to be connected. So I've got to keep everything connected to here. So I don't know, for example, this is a tree. Right, I can't add, so like if I add an edge here, that's not a tree anymore. That would be a cycle because I could go around there. But everything is connected, there's no cycle, so this is a tree. So my challenge to you is draw a few example trees, play around with this, and count how many vertices they have and how many edges they have, and see if you can make a conjecture as to some kind of relationship between the number of vertices and number of edges if you have a tree. And then you can also think about, once you have your conjecture, how could you possibly prove that?